Hi everyone. So today I made a little video, or I'm making a little video, dealing with implicit differentiation. Implicit differentiation means that there's something implied. We talked about this a little bit in class, but because we had to spend half the class in the auditorium, I figured we should use a video to cover the rest of class. So just to review, when we're doing implicit differentiation, like x squared plus y squared equals 9, say this circle, I'm just going to take the derivative of each piece. So the derivative of x squared is 2x, plus the derivative of y squared is 2y times the derivative of that inside y function, the derivative of that inside y function with respect to x. And the derivative of 9 is 0. Of course, I'm doing this same chain rule approach here that I'm doing here. You just don't see it because, well, if we bring the 2 down in front and leave the inside function alone and subtract 1, and now we come back and we take the derivative of that inside function, which is called x, with respect to x, dx is always 1. So we end up with 2x plus 2y dy dx equals 0. So that's step 1 of implicit differentiation. You want to take the derivative of everything with respect to x. Now we still need to solve for dy dx, because that's what we're looking for when we take a derivative. We want to know what the derivative is, so our answer isn't done until it says dy dx equals. Alright, so make sure you keep going until it says dy dx. So I'm going to have 2y dy dx equals negative 2x, and divide both sides by 2y to get dy dx equals negative x over y. Okay, there's the first derivative. Nice. Any questions? No, I guess we can't do that now. But what we can do is, what if we want to take the derivative of this? What if we want the second derivative? Oh, yes, please notice, when you do implicit differentiation, don't be surprised if you have y's showing up in your answer. Okay, so if I want the second derivative, or the derivative of dy dx, notationally, dy dx equals negative x over y. Okay, so then I want to say, hey, let's take the derivative of this again. So take ye the derivative of the derivative. Take ye the derivative of negative x over y. Derivative twice of y with respect to x both times. Okay? And then over here, when I take the derivative of this, I notice I have a quotient over here, so I have to use quotient rule. Low, d high, the derivative of negative x is negative 1, minus high, d low, the derivative of y with respect to x. This is d low. Low is y. I want the derivative of low with respect to x. So that's just dy dx, all over low squared. Now, there's some tidying up that we can do, and there's some tidying up that we must do. See this dy dx over here? Well, it can't stay. Remember how we said originally that dy dx was negative x over y? We have to substitute that in. So while I tidy up these signs, I'm also going to replace dy dx with negative x over y. And so I have negative y plus x, negative x over y squared. Or negative y minus x squared over y squared. You could stop here, or if you wanted, you could make a common denominator up on the top. And so this would be negative x squared plus y squared over y squared, so over y to the third. But this blue step here would be sufficient. You can't stop here. And I'd grimace if you stopped here. This is okay. You don't need to make the common denominator. All right? So that's implicit differentiation. I just wanted to go through a couple of more problems with you to see how, if you can get a little more comfortable with this. We will be doing a partner activity when we're in class next. So how about 4x to the third plus y to the third equals 2xy plus x minus x squared y. That looks heinous. And I want to find dy dx. Find dy dx. Okay? So the derivative of 4x to the third is 12x squared. Now the derivative of y to the third, I take the derivative of the outside cubing function. I leave the inside y alone. But now I come back and I take the derivative of the inside, the derivative of that inside function with respect to x. Okay? So this, let's use a different color. The derivative of this is all of this. Then we come to our equal sign, and oh look, I see a product. So I'm going to use the product rule. And I'm going to choose to group this as 2x and y. So this times the derivative of that. 2x times the derivative of y is called dy dx, plus this times the derivative of that. So all of this is the derivative of that piece. Now, we've got our plus sign. The derivative of x is 1. And another product. And it's behind a minus sign. So I'm going to do the product rule, and when I'm all done doing the product rule, I'm going to distribute the negative throughout. So minus the derivative of this times that, 2xy, plus the derivative of that times that, x squared dy dx. Okay, so I need to distribute that negative, and that's going to give me 12x squared plus 3y squared dy dx equals 2x dy dx plus 2y plus 1 minus 2xy minus x squared dy dx. So at this point, I want to move all the dy dx's to one side and all the not dy dx's to another side. All right, so I'm going to choose to move the dy dx's over here and move this thing over here. So I'm going to have 3y squared dy dx plus x squared dy dx minus 2x dy dx equals 2y plus 1 minus 2xy. And don't forget to move this guy over, minus 12x squared. Now on the left-hand side, I can factor out a dy dx. 3y squared plus x squared minus 2x equals 2y plus 1 minus 2xy minus 12x squared. But dy dx isn't by itself yet. All this stuff is attached with multiplication. So if I want to get dy dx by itself, I have to divide by all this stuff. These will cancel. I'll have dy dx by itself, and all this stuff. I don't see any like terms to combine on top or on the bottom, and don't you dare cancel these y's or these x's. That is so pool noodle. No pool noodles. No. Okay, so there's implicit differentiation. Now we may also be called upon to do our implicit differentiation to find the derivative at a point, like if I were going to write the tangent line. So if I have x squared plus y to the third equals 18xy, and I want to know the slope at 0, 1? No, that doesn't make sense. Oh, yes, it does. At 0, 1. Okay. But no, that doesn't make sense. At 0, 0 is what I'm going to go with. There we go. Okay, so I first need to, because if I plug a 0 in here and a 0 in here and a 0 in here, I get 0 equals 0, so I know that the stuff is equal to each other. All right, good. So this is my ordered pair. In order to write a tangent line, I need not only an ordered pair, but a slope at a point. So I need to find dy dx at 0, 0. So that means I'm going to need to find dy dx. So let's find dy dx by taking the derivative implicitly. The derivative of x squared will be 2x. And of course, you can represent this chain rulily. The derivative of the inside function with respect to x, but that's just going to be 1, plus, take the derivative here, bring down that exponent of 3, subtract 1. Now come and take the derivative of the inside function with respect to x. And over here on the other side of the equal sign, I see a product, and I'm going to choose to do this as 18x times y. So I'm going to have 18x times dy dx plus the derivative of 18x is 18 times y. Now we still need to solve for dy dx. Oh, and dx is 1. 3y squared dy dx equals 18x dy dx plus 18y. And I want to move all the dy dx stuff to one side and the not dy dx stuff to the other. So I'm going to have 3y squared dy dx minus 18x dy dx equals 18y minus 2x. On the left side, I'm going to factor out a dy dx, giving me 3y squared minus 18x equals 18y minus 2x. And then I'm going to divide both sides by 3y squared minus 18x so that I can get the dy dx by itself. Okay, so these will cancel. I'll have dy dx. Now notice we want to evaluate our derivative at 0, 0. Oh, Mr. Kukla, you didn't pick a good number. All right, let me see if I can somehow recover this. Yeah, blah. Sad face, sad face. God, can we just do... No, we can't. If I make... Sorry. I paused the video now, but it won't let me pause and continue. I'd have to start over or make a second video, and I'm not doing that. So if I made this 2, 1, this would be 4, and this would be 1. This is 5. If I plugged in a 2 and a 1 here, I would have 2, and so I want this to be 5 halves. Ooh, I like that. Because then if I plug in a 2, those cancel, and I get 1 times 5 is 5, and 1 plus 2 squared, all right, 2, 1. 2, 1. But the 18 is gone, so the 18s are gone. 18s are gone. 18s are gone. 18s are gone. Okay, so now let's plug in our 2, 1, and hopefully this will work. So we're evaluating dy dx at 2, 1. So if I plug in my 1 and my 2, I get 1 minus 4 on top. And if I plug in my 1, I get 1 squared times 3 is 3, minus 2 on the bottom, or negative 3 over 1. So I know that dy dx at this point is negative 3. And therefore, the tangent line equation shouldn't be so terrible for us to write. It's going to be y minus 1 equals negative 3 x minus 2. A word of caution here. On the last test, there were a couple of students who did not write the tangent line properly. They did this very interesting thing. So let's see what they did. Okay, so here's our dy dx. And they would have done something like this. Y minus 1 equals y minus 2x over y squared, 3y squared minus x, x minus 2. No, that's really, really quite terrible. You can't just shove the derivative in here. It's the derivative at a point. You have to plug the ordered pair in and put the result there. This is not good. This is, oh, we're going to be sad today. If we do that, we'll lose lots and lots of points. So don't do that. Evaluate the derivative at the given point and then plug that slope in. So my answer to what's the tangent line here is simply that. Okay? All right. So let's see about doing some second derivatives implicitly. How about 2x to the third minus 3y squared equals 8? Okay, second derivative. Well, in order to find the second derivative, I first need to find the first derivative. So I'm going to bring that 3 down, and 3 times 2 is 6x squared. Don't forget to subtract 1. I can't tell you how common a mistake this is when you take this derivative. Bring that 3 down, get the 6, but you have to subtract 1. Here, the derivative of 3y squared, I'll bring down the 2, I'll have minus 6, leave the inside function alone. I'll subtract 1 times the derivative of that inside with respect to x. And the derivative of 8 is 0. So I'll move the dy dx stuff to one side. I'll have 6x squared equals 6y dy dx. And then I'll divide both sides by 6y. And so I end up here with dy dx equals x squared over y. But I don't want the first derivative, I want the second derivative. So if I'm going to do the second derivative, I need to use the quotient rule here. So the second derivative will be low d high minus high, the derivative of y with respect to x, over low squared. And yes, I'm not done as long as there's a dy dx here. I have to replace dy dx with what dy dx is equal to. And so I'll have 2xy minus x squared times x squared is x to the fourth over y squared. You don't have to make a common denominator up here if you don't want to. You can stop at this point. You may not stop at this point. This would be sad face. This will be smiley face. And you could certainly do 2xy squared minus x to the fourth over y to the third if you really wanted to tidy this up. Okay? So there's the second derivative. How about something tricky? How about 2y equals x squared plus sine y? Not sine x, sine y. All right, so the derivative of 2y, well, that's 2 times the derivative of y with respect to x. The derivative of x squared is 2x. Of course, we could write it as 2x times the derivative of the inside x with respect to x. And the derivative of sine is cosine. Leave the inside alone because of chain rule. Come back and take the derivative of the inside with respect to x. Okay, now move all the dy dx's to one side. I think I'm going to move them over there. 2 minus cosine y times dy dx equals 2x. And so dy dx equals 2x over 2 minus cosine y. All right, there's the first derivative, but wait a minute, I wanted the second derivative. So let's have a second derivative. For my second derivative, I need to use the quotient rule. Okay, so the second derivative will be low d high, the derivative of the top will be 2, minus high d low. The derivative of 2 is 0. The derivative of negative cosine is positive sine. Leave the inside alone. Now come back and take the derivative of that inside with respect to x. So low d high minus high d low all over low squared. And don't forget, we have to replace this dy dx with dy dx. So I'm not quite done yet. Oh, I wish I hadn't done that. Okay, so the second derivative then will be 2 minus cosine y minus 2x sine y times, what was our first derivative? It was x squared over 2 minus cosine y all over 2 minus cosine y squared. Please, this is on the bottom, this is not on the bottom. You cannot cancel one of these with one of each of these. Please do not do that. You could tidy this up and make x to the third if you want. I'm probably just going to leave it here and walk away. You could make a common denominator here. You still wouldn't be able to cancel one of these. Just move on with life, okay? All right, so there is our implicit differentiation. So next, let's take a quick look at review. Speaking of y equals 2x minus 5 to the third times 3x plus 4 to the second, let's take the derivative of this. It's product rule, but it's also chain rule, right? I've got a product and I've got functions inside of functions. So I'm going to be thinking product rule when I do this. This times the derivative of that. dy dx equals this times the derivative of that. Well, the derivative of that requires chain rule. I have to bring down the 2, leave the inside alone, subtract 1, times the derivative of the inside function. Plus, that's only the first half of the product rule, this 3x plus 4 squared times the derivative of this piece over here. Bring down the 3, 2x minus 5, subtract 1. Again, a lot of people are going to leave that 2 off. That's a 2 there. It was 3. It's got to go down by 1 times the derivative of the inside function. There's our product rule. Now, this may look familiar to you as something that we saw a bunch both at the beginning of this school year, but also last year in pre-cal when it was time to factor. Why, look, a factoring opportunity. I can pull out a 3x plus 4 to the first and a 2x minus 5 to the second. What's left over? Well, one of these, and this 2, and this 3. Then our plus sign. We took out one of these, we took out both of these, we still have the 3 times the 2. Ooh, I guess I can pull out a 6 as well. And so when I combine like terms, I get 5x minus 1 times 2x minus 5 times 3x plus 4 times 6. Now, we can stop here with free response. But multiple choice, this will be our answer. And in chapter 5, we're going to be setting this derivative equal to 0, which is going to require us to factor and set the factors equal to 0 to find some critical points at 1/5, 5/2, and -4/3. If we don't factor this, we'll never be able to find our critical points in chapter 5. So this is coming. Be ready. This is why we were doing these problems last year where we were factoring, because very soon now you're going to have to set this equal to 0. And I would much prefer to set this equal to 0 than to set this equal to 0. Okay? All right, so that was product rule with chain rule. What about 2x minus 5 to the 3/2 over 3x plus 4 to the 1/2? So here's y, and I want dy dx. So that's quotient rule, right? I see something divided by something. So I'm going to use low, 3x plus 4 to the 1/2, d high. Now I have to take the derivative of this. I'll bring the 3/2 down in front. I'll leave the inside alone. I'll subtract 1. 3/2 minus 2/2 is 1/2. So we did low, d, high. Oh, we forgot to come back and take the derivative of the inside. Watch out for that. Okay, so low, derivative of the outside, derivative of the inside, low d high, minus high, 2x minus 5 to the 3/2, d low. So the derivative of this, I'll bring down the 1/2, I'll leave the 3x plus 4 alone, I'll subtract 1 up here, but then I have to come back and take the derivative of that. The derivative of 3x plus 4 is just 3. Done. Of course, in chapter 5, we'll be setting this derivative equal to 0 and finding out when this derivative is undefined. So why don't we practice factoring out the lowest power on the factor? So a 3x plus 4 to the -1/2. And, ooh, these will cancel. I also notice that I can pull a 3 out. And I notice that I can pull a 2x minus 5 to a +1/2 out. So what's left over? Well, these canceled, this was factored out, this was factored out, and we factored a -1/2. So we've got 3x plus 4 to the first. Now we've got our subtraction symbol. We factored a 1/2 out. So we've got a 2x minus 5. We took out the 3. We took out all of this. We still have the 1/2. So let's distribute that 1/2 and combine like terms in here. We'll have 3x plus 4 minus x minus a minus is plus 5/2 times that 2x minus 5 to the 1/2 and that 3x plus 4 to the -1/2. So here we've got 2x 8/2 plus 5/2 is 13/2 times 2x minus 5 to the 1/2, 3x plus 4 to the -1/2, and a 3. You could factor a 1/2 out here if you wanted. I think I would leave it here myself because I'm just going to set factors equal to 0 to find some critical numbers. This is when the derivative is equal to 0, 5/2, and -13/4, and the derivative is undefined when the denominator, that's the negative exponent, is equal to 0. and so negative 4/3. Here's when the derivative is undefined. Here's when the derivative is equal to 0. Okay, well, I hope this was a useful quick review for you, and I look forward to doing more implicit differentiation with you in class. Take care.